Alright, AP Physics students, tomorrow you will be doing your first lab in class. And I'm making this video pretty far in advance because of what happened the first night, where a whole bunch of people couldn't access the video and students were all like, ah, because they didn't know what to do. So because I'm making this video very far in advance, I'm not sure exactly which lab we'll do. I have two in mind, and I'm trying to decide between the two. But either way, you will need to know how to graph data. In fact, the point of this first lab is really just to teach you how to graph data. So it doesn't matter so much what the lab is, as long as you get data to graph. And I've discovered last year that making graphs is just a real weak point, and really confusing for students. So I'm going to go through this video. We'll probably also spend some time talking about it in class, so be ready to ask questions especially. Alright, our goal in this video is to take this set of data over here and put it onto a graph. I think the best way for us to go through this is for you to probably take about the top 2/3 of that grid paper section on your notes and make this graph with me, and then make notes to yourself around the graph about what exactly I did. So I'm going to go through this really slowly. You're going to have a chance to draw along with me. You do need to save the last the last third of your notes page, because I'm going to ask you to do a graphing problem on your own at the end of this video, and you're going to do it at the bottom of the page. So if this is the little grid section on your notes, you want to divide it 2/3, take your notes up at the top, and then at the end of the video you're going to make a graph. Alright, here we go. Step 1 in graphing is to determine the best scales for your axes. That means, what number do I need to start at here, end at here, start at here, end at here, and exactly how much does each one of these little jumps, these dashes, how much does that represent? I've got to figure that out. Now at this point, you're probably starting to draw this graph on your grid paper. As you do that, for both the horizontal and the vertical axis, you want to keep this spacing right here, so the spacing between the dashes, the same. So if you start out doing 2 boxes right here, you got to do 2 boxes right here too, and so on. If you start out doing 1 box, keep it at 1 box. The same is true for the vertical axis, but you can use a different scale on the vertical than on the horizontal. So you could do 2 boxes on the horizontal axis, the bottom axis, 1 box for each dash on the vertical axis, and that's no problem. It can get more confusing. I would say for simplicity, just make every dash represent the space between 2 boxes. Alright, now I've got to decide what number to put to start my graph and end my graph. Now let's focus on the horizontal, or the x-axis first. So from here forward in the video, I'm going to call the horizontal axis x. You got to make sure you keep it up. Alright, by convention, so just by what physicists typically do, you normally write data x, y. So this first column will almost always represent your x data. And now we're going to try to figure out what scale, or how big, my x-axis needs to be. To do that, I'm first going to look at the lowest and highest number in the x column. I see the lowest number is 20 centimeters, and the highest number is 100 centimeters. So my graph has to start at least at 20 and end at least at 100. Alright, I have chosen to make my horizontal axis, my x-axis, go from 0 to 100. That just seemed to make the most sense, since my bottom number is close to 0, top number is close to 100. Also, by convention again, almost always, where your axes intercept, where x touches y, that's called 0. And by the way, I'm afraid I didn't say it before, I'm going to call this vertical axis from here forward y. Remember, I'm calling the horizontal x, I'm calling the vertical y. Alright, now I'm going to look at my y data and figure out the scale for it. It goes from 11 to 92. Well, you know that bottom number and top number are pretty close to what they were in the drop height column, so I'm just going to go ahead and use the same axes. So notice I have now labeled my maximum, or the top, on the vertical axis. Whoops. On the vertical axis, 100. Alright, once you have determined the scale for your axes, the next thing you need to do is label them. So take a minute and look at this cartoon. Hopefully by reading it and potentially laughing a little bit, you will get it stuck in your head why you have to label your axes. Alright, guy says, I think we should give it another shot. Girl says, we should break up, and I can prove it. And then she shows him a graph of their relationship. Looks pretty bad. The guy says, huh, maybe you're right. And the girl replies, I knew the data would convince you. Guy says, no, I just think I can do better than someone who doesn't label her axes. So if you look back at her graph, her axes have no labels. I have no idea what these parts of her graph mean. And so when you make a graph, you will always label your axes. And I will show you next how to do it. Alright, so we have determined the scale for our axes. They go from 0 to 100. We finally, before we're ready to label our axes, need to decide how big each one of these little jumps right here is going to be. And since our data goes from 0 to 100, I'm just going to go ahead and make each little jump 10 centimeters. That seems to make the most sense to me, since most of these numbers are near a 10. Alright, so notice I've labeled one of the boxes 10, and the computer for some reason has also labeled this one here, but you can safely ignore that number. Alright, if you just label one dash on either axis, anyone who reads your graph is going to assume all the dashes mean that same number. So just by putting 10 on that one dash, everybody's going to know that each dash represents 10 of whatever units I'm using. Next up, I have to actually label my axes. Remember I said this is usually graphed x, y. So what I will do is simply take the labels from my chart and use them to label the x and y axes. Alright, notice what I've added to the graph. I put drop in centimeters down here at the bottom. I put bounce in centimeters over here at the side. Not the prettiest thing ever, but my axes are clearly labeled, including someone would know what units I'm using, centimeters. Very important. Alright, axes scaled, axes labeled, ready to graph. So I will take this one data point at a time. These are listed in x, y pairs. So I'm going to graph 20 and 11 as an xy pair. Now if you're used to your math classes, what I'm about to graph is this point here. 20, comma, 11, x, comma, y. Alright, so on my x column, I will find the place where 20 is, and then go up to, on y, to about where 11 is, which is clearly a little over 10. I'll plot my first point there. Alright, I did clean up the graph a little bit just so I didn't have dots all over. So I've got my 2011 point plotted. Not necessarily perfect, but, you know, hard to draw on an iPad. Next I'm going to go for 40, 35. So I'm going to find 40 on the x-axis. 10, 20, 30, 40, okay. And then about 35 on the y-axis. 10, 20, 35. 40, 35 should be somewhere around here. Alright, hopefully you got how to plot the points. I'm going to stop drawing on the graph, or stop drawing me counting the dashes, and just go ahead and plot the rest of the points. So next I've got 60, 50, which is somewhere in here. And I've got 80, 70, which is about here. And 192, so 192. I think I messed up a dot somewhere, but you get what to do. Once you have plotted your data, you're going to draw a best fit line. Now, best fit line does not mean try to connect the dots. You want to have about as many dots above the line as below it. And you're not going to try to force the line to go through the origin. So it does not have to go through this point here. it needs to match the data, these dots up here, as best it can. So ideally what you do to draw a best fit line is you take a ruler and you try to get it so you can see about half of each dot. Now that's not going to work out perfectly, so you want to try to get as many dots hidden as not hidden. So I've got to lay down the ruler so that there are as many dots that I can still see when the ruler is on top of them, as there are dots that I cannot see. So the ruler needs to cover just as many dots as it does not cover. And then I'm going to try to get the line to go through wherever the ruler is. Remember, it doesn't have to touch each dot. It just needs as many dots above it as below it. And that's not perfect. I've got a much better one on the next slide. That's how you draw a best fit line. Right, the great thing about a best fit line is we can now ask questions. So notice we only dropped our ball from 100, 80, 60, 40, and 20. Well, what if I want to know what will happen if I drop a ball from 70 centimeters? In that case, I find 70 down here on my x-axis. So 1, 2, 3, 4, 5, 6, 7. And I go up to where my best fit line is. And now I can say, well, if I had dropped the ball from 70 centimeters, it would have bounced to about, what is that, 10, 20, 30, 40, 50, it would have bounced to about 60 centimeters. We can make predictions with a best fit line. That's how they're used. That's why they're important in physics. Now up on this page I have a general rule that you should follow for your lab reports. In general, a graph should take up about the width of a page. So however wide your lab notebook page is, when you do your lab graph tomorrow or the next day, it should take up about the width of a page. And as far as height, it needs to be at least half a page in height. I'll cover this more in depth with you as you start writing your lab report though. This graph is not showing up very pretty, but there are a few things we need to talk about. First, independent variables. Independent variables are always the things you measure, usually drawn on the x or horizontal axis. Thing you measure, thing you control. So even though we would have measured both of these, and the students in CP last year will especially remember that, the thing you control is graphed on the x-axis. So if we're dropping something, we control how high we drop it from. The independent variable. The thing you control, the thing you can change. Dependent variable. That's drawn on the vertical axis, and that is the thing that is affected by your change. So the more I change the drop height, the more the bounce height changes. The bounce height depends on the drop height. And so the thing that depends is a dependent variable. Also in physics, we generally use the phrasing y versus x. So if I wanted to talk about this graph, I would say bounce height versus drop height, because bounce height is y, drop height is x. So it's y, bounce height, versus x, drop height. And that's just a common phrasing. So anytime you see something written, one thing versus another, the graph of it would be the first thing on the y, and the second thing on the x. Here are some examples of drawing best fit lines. Things I want to point out to you here. Notice that on the graph on the left, the best fit line doesn't actually touch any of those dots, but it does go right between them. And that's what a best fit line is supposed to do. Have as many above or below-ish. Here we've got one touching, but the rest, it goes through them, goes through the middle of them, but doesn't touch them. So some examples of best fit lines. After you've graphed data and found its best fit line, you now need to find the slope of the best fit line. Now, something I was really bad about in explaining to my college prep class last year, so if you had me last year, make sure you're paying attention. When you're finding the slope, do not use the data from your data table. That is incorrect. You should use the data on this best fit line. So, when you're finding the slope, forget about the data table. Act like it does not exist. Instead, pick 2 points on your line, and it's best if they are not data points, because otherwise you're tempted to come back to this data table, which remember, we're not using. So I'm going to pick this point here. And the reason I chose that point is because it's right over an x value. So that means that's going to be easy on me later. And with that point, there's also a corresponding y value. Okay? To find the slope, you've got to have 2 points. I'll do the other one in a different color. So next, I'm going to pick this point here, again because it's right over an x. It matches with a y value. So step 1 in finding the slope is pick 2 points. Now I need to write down the coordinates for each of my points in x, y form. So the point that is blue has coordinates 30 centimeters, 30 centimeters. How very convenient. Alright, next up, my green data point on the line has coordinates 70 centimeters in the x and looks like 61 in the y. Okay, so you might want to note those numbers. I'm going to switch to a blank slide so I can do the slope calculations. Also, go ahead and copy down this formula here. I'm going to reference it once I switch. So if you need to pause to copy some things down, please do that now. In physics, we use the letter m to represent slope. In your math classes, you've probably seen the formula for a line y equals mx plus b. That m was the slope. Slope is change in y over change in x. If on the last slide you were confused about those triangle-looking things, those are the Greek letter delta, and they mean change. So you would read what I have written on the screen, m equals change in y over change in x. To calculate the change in y, you pick 2 y points and subtract them from each other. We'll just call them y2 and y1 for now. And then you pick 2 x points. However, whatever y you pick, you have to pick the x that goes with it. So if for y2 I pick 61 centimeters, the x that goes with it is 70 centimeters. Now it'll make more sense as we go along. This formula I've just written, y2 minus y1 over x2 minus x1, is also sometimes called rise over run. How far over something goes, how far up something goes, divided by how far over it goes. Right, so let's go ahead and calculate that. Remember, whichever y I choose to use, the green or the blue one, if I use a point for y2, I've got to use that same point for x2. So if I use the 61 centimeters on the green for my y2, I've got to use the 70 centimeters on the green for x2. It doesn't matter which one you pick, the blue or the green, to be the coordinate for y2 and x2. If I pick green to be y2 and x2, I'll get positive number divided by positive number. If I pick blue, I'll get a negative number divided by negative number. The math-minded people can probably see that pretty quickly. If you don't, it's not that important. Just know it doesn't matter which point you pick, as long as whichever one you use for y2, you also use for x2. So let's do that. I'm going to use the green point, the green lines we drew on the last one, for coordinate 2, just so I can keep all the numbers positive. It's usually less confusing for people. So the green y coordinate is 61 centimeters. The green x coordinate is 70 centimeters. And then I'm going to subtract the blue coordinate from those. So the blue y, which I'm using as y1, is 30 centimeters. The blue x is also 30 centimeters. Alright, subtract, I get 31 centimeters over 40 centimeters. Now, hopefully your slope can be reduced to something, but this one, I'm not seeing anything that I could simplify that fraction to. So, this is okay as my slope. Since we just talked about dimensional analysis though, there is one thing I could do. Since these are both centimeters, those units will cancel. And so I will have a dimensionless slope, no units, of 31 over 40. Alright, that's how you calculate slope. This is going to be something we're going to do a lot. You want to make sure you get it right, get it tight on this first lab. So if you need to watch this video part again on how to calculate slope, feel free. When we go to the next slide, I'm going to ask you to, on your own, calculate a slope, or graph data and calculate a slope. So you're going to be doing a lot on your own on the next slide. Alright, so I told you to save the last third of your note-taking page because you're going to need some grid paper. I've given you some data points here. They're a little harder than the ones I did because they have decimals in them. So what I want you to do is, on your own, in that last third, graph this data. So graph, step 1, graph. Step 2, I want you to do a best fit line. And I want you to find the slope of the line that you draw. So graph that data, find the best fit line, and then find its slope. Hint, remember, we're going to do x, y. It's usually first column x, second column y. Pretty much always how physicists list data. So you need to figure out the scales for your axes, you need to plot the points, you need to label your axes, draw a best fit line, and get that slope. This is probably going to take you like 10 minutes to do. So in the bottom third of your page, do that, and when you come back, I will show you my graph. So pause the video now, you don't want to spoil it by seeing mine. Alright, so here's my graph, and I'm going to walk you through what I did. So first, in scaling my axes, I noticed that my mass only went to about 3.5, and so I made each of these dashes along the bottom half a kilogram, okay, which put my maximum at 5 kilograms. My force, however, went almost to 9, so I made each of my dashes on the vertical, the y column, 1 Newton. Even though you don't know what a Newton is yet, it is a unit. Right? Then I plotted my data points, boom, 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 drew the purple best fit line, and I picked 2 points on that line. You do not have to pick the 2 points that I did. No matter which 2 points you picked, you should get the same slope I got. Right? So for my 2 points, it was 6 newtons and 2.5 newtons for my first xy pair, and then 2 newtons, 0.75 kilograms for my second xy pair. And then if I carry out the calculation for my slope, grab a calculator real fast, I'm going to get 2.29 newtons per kilogram. And I'd say on your first attempt graphing and finding a slope, if you got between 2 and 3, you're doing pretty good. Notice that I included units on my slope, newtons per kilogram. On the last one, centimeters and centimeters cancel, but here they did not, and units don't just go by themselves, so slopes often have units. Important thing to remember. Alright, we will do a lab tomorrow, and you will be expected to graph data. Do make sure that you have done the before reading and after reading question before coming to class tomorrow. That's all, and I hope we have a fun first lab. Good night.